In this video, we're going to talk about geometric series. Generally, it's hard to find what the series sums to. So for example, if I had this series, the sum from 1 to infinity of 1 over n squared, if I plug in 1 into this, I'll just get 1. If I plug in 2, I get 1/4, and then I get 1 over 9, and so on. And this series looks kind of harmless and not too bad, but it's actually really tough. It's really tough to figure out what this sums to. It turns out the most sort of standard way of figuring out what it sums to is to use something called differential equations. And what the sum actually is the sum is pi squared over 6, which is just kind of bizarre. Like there doesn't seem to be any sort of pi showing up here at all, but nonetheless, it does sum to something that has a pi in it. So, okay. There's two special types of series where the sum is actually easier to compute. And one of those is called a geometric series. The other one's called a telescoping series, which we'll talk about in the next video. So a geometric series has this form. There's some initial term a, and then to get the next term, you multiply it by some number, which I'm going to call r. And then again, to get the next term, I also multiply by r. And you keep going like that. You keep multiplying by r again and again and again. And if I go forever like this, I get this infinite geometric series, and I can write that in sigma notation like this. Like for example, if I plug in 0 for this n, r to the 0 just becomes 1, and I get a times 1, which is a. I get my first term. And if I plug in the subsequent values, I'll get each subsequent term. So in this series, I'm going to specify that I want a to be not 0, because if I started with 0, and I multiplied it by anything, I would just get 0 plus 0 plus 0. And that's not very interesting. And this number that I keep multiplying by, I call that r, which is the common ratio. So there's a really nice way to find the sum of a geometric series. So I want to talk about that. So if I just took the first n terms, that's the nth partial sum. I'm calling it S sub n. What can I do with this? So I'm going to multiply both sides by r. So if I multiply this side by r, I get this. On the other side, I'm going to multiply each term by r. So a multiplied by r gives me ar. Ar multiplied by r gives me ar squared. And if I keep going, the second to last term, that would multiply by r to give me this thing. And the last term multiplied by r, that would give me ar to the n. So now to exploit the fact that I have a bunch of these terms being the same in both of these equations, I'm going to subtract the two equations. And when I do that, on the left, I get S sub n minus r times S sub n. On the right, the ar's cancel, ar squareds cancel. In fact, everything in the middle cancels up until these two. The only thing that doesn't is I have an a up top, and then minus, there's this ar to the n from the bottom. So okay, I can factor out S sub n on the left times 1 minus r. Factor out an a on the right times 1 minus r to the n. I was trying to figure out what's this nth partial sum. So to isolate it, divide by 1 minus r. I get S sub n equals a times 1 minus r to the n over 1 minus r. So I'm going to highlight this. This is a formula for the nth partial sum of my geometric series. So if I had just a finite geometric series that just consisted of n terms, this is the formula for its sum. But I'm interested in, well, what if I went forever? What if I had infinitely many terms? Is this thing going to converge or diverge? And the short answer is it depends on what r is and how big it is. One of the things I want to notice for this formula is, well, I don't want to divide by 0 here. So for me to be able to use this formula, r is not allowed to be 1. Okay. Okay. So I'm going to split this up into two cases now. So two cases. In the first case, I'm going to suppose that the absolute value of r is less than 1. So if that was happening, that would mean r is between -1 and +1. It can't be equal to them, but it could be in between. So I'm imagining numbers like 1/2 or -0.2. And if I have numbers like those and I raise them to this power and I let that power go to infinity, that's going to get really, really small. It's going to get really close to 0. So my whole fraction So my whole fraction, if I take this limit as n approaches infinity of this nth partial sum of s sub n, well, I got that a, and then I get times 1 minus the r to the n gets close to 0, so I get to replace it with a 0. And on the bottom, I have my 1 minus r. So this just becomes a over 1 minus r. In fact, that's what it summarizes in the box for me. This geometric series converges if the absolute value of r is less than 1. And when that happens, the sum ends up just being a over 1 minus r. A over 1 minus r. Okay. The flip side is, well, what if the absolute value of r is actually greater than or equal to 1? So now we're talking about numbers that are either bigger than or equal to 1 or less than or equal to negative 1. So let's ignore the possibility that they could be 1 or negative 1 first. If it was something bigger than 1 or smaller than negative 1, when you multiply by r again and again, you're making the whole thing, ignoring negative signs, larger. So you add bigger and bigger and bigger terms. And when that happens, it's actually impossible to make the whole thing be finite. If r was just 1, then you keep multiplying by the same thing. So the first term is the same as the second, is the same as the third. You keep adding the same number to itself again and again. It's just going to get bigger and bigger and bigger. When r is negative 1, I'd encourage you to pause the video for a minute to think about that. In 3, 2, 1, pause it and think about that. I won't talk about that like right now, but if you have questions about it, I'd encourage you to bring them in. We'll explore that later actually in our course. But it turns out even then, the partial sums don't settle in on just one value. They keep kind of bouncing around between two things. So it won't converge. So if r is greater than or equal to 1, the series diverges. So the whole thing, this diverges. And in my box, it does say that as well. Okay, so how do we use this? Let's do some examples. So I want to determine if the series converges or diverges. If it converges, find the sum. Okay, so I got this sum from 0 to infinity of 1/2 to the n. So to get it started, I'm going to plug in some values. So if I plug in 0 for n, I get 1. And then plus, if I plug in 1, I get 1/2. If I plug in 2, I get 1/4. And then I keep going. I get 1/8 and so on. So first I asked myself, well, is this geometric? Is there a common ratio? So to get from the first term to the second, well, I multiply by 1/2. Then to get from this one to the next term, oh, I do multiply by 1/2. In fact, I keep multiplying by 1/2 again and again and again. So it is geometric. I like that. So based on what r is, I want to give you a quick minute to say, does it converge or diverge? And if it converges, use this formula to get the sum. So give a quick pause for 1 minute to try that. In 3, 2, 1, pause it and try that. Okay, so hopefully you did that. Hopefully you paused it to try it. So the first term is 1. R is 1/2. So, well, the thing I care about is, well, the absolute value of r is also 1/2. That's smaller than 1. It's smaller than 1. So it converges. It converges. And its sum is going to be given by my formula a over 1 minus r. So the a is 1, and then over 1 minus r is 1/2. So this simplifies to 1 over 1/2. Oh, and that's 2. That is 2 right there. In fact, you might have recognized the terms in this series because we actually looked at this exact example in the last video. That exact example. And we actually showed 2 different ways of explaining, well, why is the whole sum just equal to 2? Now we have a third way, using geometric series. Okay, so let's end the video with a final example, but let's up the difficulty. So let's say I have this series. So, okay. In fact, okay, I want to make one quick comment about the previous one before I tackle this one. One of the ways I can tell that this thing is geometric, just by looking at the formula, is I see this like some number to the n power floating around here. And that seems to happen in my geometric series formula. I don't see quite that in this problem. Like I see something to the n plus 1, and I see something with a 2n here, which is not quite just n. So maybe it's geometric, maybe not. So to get this started, I can plug in some values to figure out what the first few terms are. So if I plug in n equals 2, I'll get negative 7 cubed over 3 to the 4. And then plus, if I plug in n equals 3 now, I'll get negative 7 to the 4th over 3 to the 6th. If I plug in 4 for n, I'll get negative 7 to the 5 over 3 to the 8 plus dot dot dot. And the first thing I want to ask about this is, well, is this geometric? Like, is there some common ratio I multiply each term by to get the next term? So I want to have you give the video a quick pause for just maybe 20 to 30 seconds and see if you can determine, is it geometric or not? Is there a common ratio? Okay, so hopefully you did that. Hopefully you paused it to think about that. So it is geometric because to get each subsequent term, I multiply the previous one by negative 7 on the top and then 3 squared on the bottom. Same thing here. I multiply by negative 7 on the top and then 3 squared on the bottom. So this is geometric. It is geometric. My first term, a, is this thing right here. So I can work out what that is. Negative 7 cubed, that's going to be negative 343. So negative 343 over 3 to the 4th, that's 81. And then my common ratio r, well, that's negative 7 over 9. So, well, does it converge? Well, if I look at the absolute value of r, that's positive 7 over 9. And the key thing I care about is, well, that's less than 1. So since that's less than 1, it means this geometric series converges. It converges, so I can find its sum. I can find its sum. It's given by the formula a over 1 minus r, where a is negative 343 over 81, all over my 1 minus r, so all over 1 minus negative 7 over 9. So I get this double negative. And I could simplify this denominator. I could add these two things together by getting a common denominator. That'll give me 16 over 9. So now simplifying this, I get negative 343 over 81, and then multiply by the reciprocal, 9 over 16. I can cancel with the 9 and the 81. That'll leave me with a 9 and a 1. And now multiplying through, I get negative 343 over 9 times 16, that's 144 on the bottom. And that's my value. That's my value for what this sum is, what it converges to. Okay, so I want to end by just briefly talking about, like, when I first looked at this, maybe it wasn't immediately obvious that this thing was geometric, that it had this form. But there's a way I could have manipulated it doing some algebra to put it into that form. So if I have this sum from 2 to infinity, on the numerator, I can split that up as negative 7 to the n times negative 7 to the 1. That's the same as this, using exponent properties. And in the denominator, that's the same as 3 squared to the n power. Because if I have a power to a power like this, they multiply to give me 2n. And now I can rewrite this as the sum from 2 to infinity. I'll put this negative 7 to the 1 first. That's just negative 7. And then I have something to the n over something to the n. So I can write that as one big fraction to the n, where on the top I have negative 7. And on the bottom I have 3 squared, which is 9. And now if I look at this, well, this thing to the n power, well, this is my r right here. R is my negative 7. Oops, can't really see it. It's my negative 7 over n. That's the same thing that we got here. The only thing I would need to figure out now is, well, what's this initial term? And to get that, I would just plug in 2 for n. And if I did that and work this out, I'd get my initial term. And that would lead me to the same sum that I had before.